Alhamdulillah. Today we will study this book, uh, Introduction to Mathematical Statistics, 6th edition by Hook and Crick and M.C. Kane. Okay, we go to chapter 1. In chapter 1, we will talk about probability and distributions. First, 1.1 Introduction. Many kinds of investigation may be characterized in part by the fact that repeated experimentation under essentially the same condition is more or less standard procedure. For instance, in medical research, interest may center on the effect of a drug that is to be administered, or an economist may be concerned with the price of 3 specified commodities at various time intervals. Each experiment terminates with an outcome, but it is characteristic of this experiment that the outcome cannot be predicted with certainty prior to the performance of the experiment. If this kind of experiment can be repeated under the same conditions, it's called a random experiment. And the collection of every possible outcome is called the experimental space or the sample space. Example 1.1.1. If the toss of a coin, let the outcome tails be denoted by T and let the outcome head be denoted by H. If we assume that the coin may be repeatedly tossed under the same conditions, then the toss of this coin is an example of a random experiment in which the outcome is one of two symbols, T and H, tails and head. That is the sample space is the collection of two symbols. It is example of random experiment. We have sample space two symbols, T and H. Now let's see denote a sample space, and C letter or C small denotes an element of C, and let's see represent a collection of elements of C. If upon performance of experiment the outcome is in C, we shall say that the event C has occurred. Now convinced of our having made and repeated performance of random experiment. The ratio of F per n is called relative frequency if the event C in these n experiments. Now the number of P associated with the event C is given various names. Sometimes it is called probability, the probability that the outcome of the random experiment is in C. Sometimes it it is called the probability of the event C. Example 1.1.3. Let's see denote the sample space of example 1.1.2, and let's see the collection of every ordered pair of C for which sum of pair is equal to 7. That C is the collection. This, suppose that dice are catch and is 400 times, and let f the frequency of a sums of 7. F is 60, then the relative frequency with which outcome was in C is f per n, like this. We have 0.15. Thus, we may associate it with C as a number P that is close to 0.15, and P would be called the probability of event C. Now, 1.2 set theory. The concept of a set or a collection of subjects is usually left undefined. However, a particular set can be described so that there is no misunderstanding as to what collection of objects is under consideration. The symbol is called, or it just means that C element of C cut C letter. The notation C, like this. This notation is read C is the one-dimensional set of points X for which this X between 0 and 1. Similarly, C, like this, can be read C is two-dimensional set of points X and Y, XY, that are interior to 0.0 and 1.1. Definition 1.2.1. If each element of a set C is also element of set C2, C1 and C2, is called subset, writing like this. I repeat again that subset of two sets if each element of a set C1 is also an element of set C2. Now definition 1.2.2. If a set C has no element, C is called null set. We denote like this, writing like this: C equal H null set. It is symbol of null set. Now definition of union. The set of all elements that belong to at least one of the sets C1 and C2 is called the union of C1 and C2. And we're writing like this: C1 union a union of C1 and C2. Now intersection. The set of all elements that belong to each of the sets C1 and C2 is called intersection of C1 and C2, and we're writing like this: C1 intersection C1 and C2. These are diagram, Venn diagram, represent example of union and intersection. Figure A, it is example of the union, and figure B is represent intersection. Now we go to definition SPICE. Ascertain, discussions, or consideration the total of all elements that pertain to the discussions can be described. The set of all elements under consideration is given a SPICE special name. It's called the SPICE. We shall often denote SPICE by letters such as this, C and D. Now, complement. Let C denote the SPICE, and let C be a subset of set C. The set that consists of all elements of C that are not elements of C is called the complement of C, actually writing respect to C. The complement of C is denoted by this, in particular like this: C complement equal null set. Now, De Morgan's laws, a set of rules which will prove useful, is known as De Morgan's laws. Let's see denote a SPICE, and let Ci subset C. I is 1 and 2. Then this C1 intersection of C1 and C2 complement, we result like this. Now it is several examples. We have functions such as fx equal to x, like this, and gxy like this, e exponent minus x minus y, and it is the border. And then function h. The value of fx at the point x is 1. We have f1 equal to, and the value of gxy at the point minus 1 and 3. We have g function is 0. Okay, now example 1.1.20. Let C be a set in two-dimensional space and let QC be the area of C. If C has a finite area, otherwise let QC be infinite. Thus, if C is two-dimensional x, two-dimensional x and y of this, then QC equal P. If C a pure set with elements 0, 0 and 1, 1, 0, 1, then QC equals 0 if like this. C two-dimensional x and y of this x greater than equal 0 and y greater than equal 0, x plus y less than equal 1. Then QC equal 1 per 2. And then we have an example. Let C be a set of three-dimensional space QC, the volume of C, and C finite volume. Otherwise, QC be indefinite. Thus, if C like this, three-dimensional x, y, and z of like this border, QC equal 6 if C like this. Then QC is undefined. At this point, we introduce the following notation: the symbol integral fx dx, one dimension. It's integral in two-dimensional, and it is symbol of summation of fx in one dimension, summation in two-dimensional, let's be a one-dimensional set and let QC like this, integral e exponent minus x dx, and Q has border, has a set C is one-dimensional x and have border this. QC equal 1 if we using this border to this integral, we will find 1. And if we use this border, we will find e minus exponent minus 1 minus e exponent minus 2. If C1 this and C2 this, Q intersection of C1 and C2 like this, C1 and C2, Yeah, we know C1 has border this between 0 to 1, and C2 has border 0 to 3, this. So the union of C1 and C2, we get this integer e exponent minus 1 dx with border 0, begin 0 to 3. And now let C be n dimensional space, and let Q C like this integral dx1 dx2 till dxn with border C. If C is set n dimensional of x1 to xn and have border like this, so if we using this border, we apply to this function, we will find this, we will resolve this and begin integral 0 1 this and 0 xn until 0 x3 0 x2 dx1 dx2 dxn minus 1 dxn, and the result is 1 per n factorial, where n factorial is n multiply n minus 1 multiply blah 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 multiply 2 multiply 3 2 and 1. Now exercise. Thank you and your attention. Assalamualaikum warahmatullahi wabarakatuh.